In today's session, we'll try and develop the equivalent circuit of a synchronous machine. And using that equivalent circuit, we'll also understand the phasor diagram of synchronous generators. To develop the equivalent circuit of a synchronous generator, per se, we have to understand uh, A, the effect of armature reaction, effect of stator windings, that will include the stator resistance and the self-inductance component. So, the rotor circuit is pretty simple since we know that a DC voltage is applied to the rotor windings. The rotor side will actually include the rotor resistance and the rotor's inductance. So this is the rotor side, that's also the field in this case, inductance and its inductance and its resistance. And we can also have some external resistance that can be used for uh, field current control in case of the DC windings. So this part represents the rotor windings of the uh, synchronous generator. Now, since there is only one rotor winding, there is no phase concept with respect to DC. So there will be only one rotor winding, that will where RF will be the resistance of the winding and LF will represent the self-inductance of that rotor winding. We can have externally a resistance incorporated in the field to control the field current. So this part represents the rotor winding. As far as the stator winding is concerned, these three things need to be taken into consideration to model the stator windings. So because of the field circuit, a voltage is induced uh, in the let the induced voltage be EA. That's EA is the voltage induced in the armature of the synchronous machine. This voltage is a AC voltage. The induced AC voltage is present in the synchronous generator. Now, as long as there is no uh, load on the armature, the current through the armature windings will be zero. So there is no, the induction machine is, the synchronous machine has unloaded, the armature is unloaded. In that case, the armature current will be zero. In that case, we can say that only uh, the rotor resistance, the stator resistance, Ra, represent here the armature uh, resistance, may not actually also show the resistance at this time. We can directly show that the voltage, the output voltage at the terminals will be equal to the input voltage equal to the generated voltage in this case. At IA, at for an unloaded condition, when we are not loading the armature, we can simply say the terminal voltage that's available to us will be equal to the induced voltage in the synchronous generator. Now, what happens once we load the system, once we are applying some sort of load onto the synchronous machine, IA no longer remains zero. There will be some finite value of armature current flowing through the stator windings. As the armature current starts to flow, once the armature current increases in this armature circuitry, we know that uh, it will produce a magnetic field of its own. Now, the DC was producing a magnetic field, that was the rotor magnetic field, because of the current flowing, because of the loaded nature of the synchronous generator. Now, the current flowing in the armature will result in the production of its own magnetic field, that is the stator magnetic field. Now this stator magnetic field is actually in opposite to the main magnetic field that was the cause of generation of EA. That was the cause of induction of EA. In this case, the rotor magnetic field. So the stator magnetic field will try to weaken the main magnetic field. This has been explained in DC machines as well. This is actually known as the principle of armature reaction. So now how can we model this armature reaction? Now what we know the effect of this magnetic field is somewhat, if we can say that initially at no load, Vt, this was the direction of Vt, this was the direction of Ea as well, as both were equal. Now once we load the system, now depending upon the load, say for example we are applying a lagging load, that means if Vt is now in this direction, the current Ia will be lagging behind uh, instead of putting Vt here, I'll put it Ea. Ea is the generated voltage. Uh, we have a lagging load here, so Ia will be lagging behind Ea. Now Ia, as I said to you, it's producing its own magnetic field. Uh, Depending upon the nature of current, that magnetic field will induce that stator magnetic field will induce a voltage in the stator windings as well. Uh, Once you are loading the system, the current Ia flows in the armature. That current Ia produces a stator magnetic field. That stator magnetic field will also induce a voltage in the armature. That voltage is actually uh, opposing the actual induced voltage because of the rotor magnetic field. Now the nature of this voltage will be such that if I represent that voltage by E stator magnetic field, the nature of that voltage will be it will be lagging behind the current Ia by 90 degrees. Now we can actually find the magnetic field and we can accordingly find the direction of induction of uh, E stat uh, because of the stator magnetic field. Uh, Now this stator magnetic field, the magnitude of the stator magnetic field will actually be less. So let me redraw this. The magnitude of E stat will be less. It will not be as much. So the net voltage, the resultant voltage will actually be Vt. The resultant vector of E stat and Ea will be Vt. Now we can see that this armature current is flowing. It's a it's an AC current flowing in the armature windings, which produces a stator magnetic field. That stator magnetic field produces another. That stator magnetic field induces another voltage in the armature windings. That's E stat. This E stat will oppose EA. So the net magnetic field in this that resultant voltage in this case, that's VT, will be the summation of the vectors EA minus E stat. Uh, we can see the nature of this voltage is such that it is lagging behind the armature. It is it is lagging behind the armature current by an angle of 90 degrees. So we can use a reactance. If E is the generated voltage, we can use XA. XA here represents a reactance that's produced because of the effect of armature reaction. So this is an armature reaction. This is a reactance produced because of the armature reactance, because of which the voltage across this, that's IA x A in this case, will be equal to E stat. Uh, Now this is one component. Apart from this, the stator will have its own resistance. Let that be RA. And the stator will have also a self-inductance. Let that be that reactance because of self-inductance be uh, X. So what we now have is the stator looks something like this. There is the R reactance because of the effect of armature reaction. There is a reactance because of the self-inductance of this coil. There is the armature resistance. Fine. Now we can actually combine XA plus X as one reactance. XS RA VT. So E is the induced voltage because of the rotor magnetic field. RA is the armature resistance. X was the self-inductance of this coil. XA was the effect of the armature reactance. We saw that because of the nature of current in the armature, a magnetic field is produced. That magnetic field induces another voltage in the armature that will be in the that will oppose the actual voltage generated in the armature windings. So XS here is the combination of these two reactances, and it is known as synchronous reactance. So in this case, EA is, if IA is the direction, is since it's a generator, IA direction of current will be like this. IAXS J times IAXS plus uh, IARA plus VT, or we can say in other words, VT is equal to EA minus JIAXS minus IARA. So this is the model of uh, this is the equivalent circuit of the stator side. So we can combine the rotor and the stator. So the rotor is simply having its own resistance and it's having its own inductance. We are applying a DC voltage here. This is the field winding resistance. This is the field winding reactance. I can now put it as XL. And there is an adjustable R. Accordingly, a voltage is induced in the armature, which has its own resistance and which has the synchronous reactance, and the available voltage to us is Vt. So in case of a generator, the direction of current will be shown like this. In case of the motor, the direction of current will be shown like this. This is for a case of generator, this is for a case of motor. And this circuit here represents the per phase equivalent circuit of a synchronous machine. What we'll actually have in case of synchronous machines is that there is only one winding of the rotor. So all the that one winding of the rotor will be uh, that one winding is actually modeled across all the three phases of the synchronous of the armature of the synchronous machine. So accordingly, our equivalent circuit, the total equivalent circuit of the synchronous machine will look something like this. So this diagram here represents the total equivalent circuit of the synchronous machine. This is for a case of a synchronous generator where IA1, IA2 and IA3 direction of current like this. Accordingly, in phase 1 we can say V51 is EA1 minus JXS IA1 minus IARA. V phase 2 will be EA2 minus J. Since the rotor is common to all the three phases of the armature side in case of a three-phase machine, in case of a single-phase machine there will be only one phase of the armature as well. So like in the case of induction machines, uh, there will be a separate rotor equivalent and there will be a separate starter equivalent. There will be all the rotor will have three phases, the starter will be having three phases, but in this case the rotor does not have any there is no concept of phase in a DC on a DC side, so the rotor winding will only be having there is only one rotor winding which is linked with all the three phases mm, of the secondary, that is the armature side in this case. So this is the equivalent circuit, and accordingly we can draw the equations of uh, for this for a synchronous generator. V51 will simply be EA1 minus JXS IA1 minus RA IA1. This will be a case of a generator, whereas in case of a motor it will simply be plus IA1 plus RA IA1. Fine. Accordingly for the second phase and for the third phase. This here is the equivalent circuit of the synchronous machines. Now using this using this equivalent circuit, we can draw the phasor diagram. Let's take this per phase equivalent circuit that we have already drawn. Um, for unity power factor, that is if we are applying a load where uh, so we start with Vt, Ia will be in the same direction as it's a unity power factor. Vt and Ia will be in the same direction. That means the voltage IARA will be in the same direction as well, and J times IAXS will be 90 degrees uh, to this. So this here will give us the resultant voltage, that is EA. So this is for the case of a unity power factor. Here our load is uh, for a lagging load. For a lagging load, let this be Vt. Since it's a lagging load, that means Ia will be in this direction and IARA will be parallel to this, and J times IXS will be at 90 degrees to this. So this resultant will be the induced voltage EA. Now this for a lagging load. Similarly, we can draw for a leading load here. Leading load, let this be Vt. Ia is in this direction. That means IARA is in this direction, and at 90 degrees to this is IAXS, J times IAXS. So the resultant will be EA. So this is the case of uh, this is the per phase equivalent circuit. Now, depending on the magnitude, we can see how Ia will vary with respect to EA. So the equivalent circuit, there are the rotor side is simple. It only has a resistance and an inductance of its own, and we can externally use a resistance that can be used to change the magnitude of current IF in this circuit. That will actually change the amplitude of this induced EMF. Now, accordingly, the stator winding has its own inductance and its own resistance. They are fairly simple, because of which with the resistance will be associated the copper losses. Uh, as well as we saw that once we load the system, armature current will flow in the system. Armature current will produce a stator magnetic field. The stator magnetic field will oppose the rotor magnetic field and induce a voltage E stat in the armature that will actually oppose the actual induced voltage EA. Now, because of the nature of this induced voltage, we can model the armature reaction effect using a reactance. I'm not saying here about whether it's an inductive reactance or a capacitive reactance. This totally depends upon the nature of the load. Uh, Now we can combine the self-inductance of the reactance due to the self-inductance of this armature winding and the reactance due to the armature reaction of this synchronous machine into one single term, that is XS. So synchronous reactance is an important term actually in case of synchronous generators, based upon which we understand the stability and the power equations of the synchronous generator. Uh, Now for the motor, it will only have the direction of armature current will be reversed as that of the generator. Accordingly, we have drawn the phasor diagrams for a unity power factor, for a leading power factor, as well as for a lagging power factor. Now, in the next session, using this equivalent circuit, we'll be able to derive the power and torque equations of the synchronous generator.